Hi everyone, my name is Emma and I'm a network software engineer from Intel. In today's presentation, I want to talk a bit about the work that myself and Harry have been doing around using AVX512 to optimize OVS packet modifications to improve performance. This work is mainly focused around optimizing the OVS Actions component of the data path. And in the past, work has been done around optimizing the DPIF, DPCLS, and NFEX parts of OVS. And for this work, I'm taking a similar approach to enhance performance of some OVS actions. So if we take a quick look at the agenda, here are some points I will be discussing in today's talk. Firstly, I want to touch briefly on OVS actions as of OVS 2.16 and the current state it's in. I'll give an overview of where actions sit in the pipeline and some issues I found that can be improved on. Then I want to talk about some of the rework and optimizations I've done around the OVS Actions infrastructure and show how implementing individual actions in SIMD can boost performance. Also, as part of this work, an Autovalidator has been put in place as a form of automated testing. So we're going to take a little look at how easy it is to test and validate this code. And finally, I will go into a bit of detail at the end on how I took an existing action in upstream OVS and added an AVX512 version of it. So with that, let's get started. So this is a high-level view of what the OVS data path looks like today in upstream OVS. And some of you may be familiar with this diagram and the previous work done around optimizing the different parts of the OVS data path. There has been talks presented around the reshaping of the data path to make it more dynamic and more flexible and generally more performant. So in the diagram here, you can see that the DPIF, DPCLS, and miniflow extracts have all been refactored to have two code paths, both a scalar implementation and an AVX512 implementation. And talks have been presented about this work in previous years of the OVS conference. And if anyone is interested in learning more details about them, you can find links to them on the OVS website. So to date, the packet parsing part of the pipeline has been optimized with AVX512. So the next logical step was to look at how we could improve performance around some OVS actions. And that is going to be the main focus of today's talk, which is the blue box on the right-hand side of the diagram, the Ovs Actions Block. So you can see that the actions block sits at the end of the data path pipeline. Your packet is going to arrive at the NIC, it'll go through the DPIF, either the scalar or the AVX512 implementation, whichever has been chosen. And once it's been parsed, it's going to arrive at the actions box, ready to be either modified, TX'd, dropped, or some action. And OVS supports a host of different actions to date, and after some investigation and performance benchmarking, I saw that these actions can be a costly part of the OVS pipeline. So the patches we're upstreaming is going to allow for faster SIMD implementations of specific actions to help cut down some performance costs. But in order to do that, we first needed to refactor the actions infrastructure to allow for an AVX512 version of this part of the pipeline. So you notice now that the previous blue actions block has changed to an action selector. I have introduced two different implementations of the OVS action block based on CPU ISA. So if your CPU supports AVX512, we can run a different version of the actions code, which is going to be more performant. Basically, we can call into this action selector, which uses a function pointer. And this function pointer can point to either the scalar path or, if your CPU allows it, the AVX512 path. So this is going to allow for a fallback scalar version of the code, which will always run on every CPU, and it will run the actions code available in upstream OVS today. And it's also going to allow us to utilize the CPU's full potential by taking the AVX512 path. And again, this is a similar approach to the way the DPIF has been optimized in the past. So by introducing this function pointer, we can now have two implementations of the actions, an accelerated path using SIMD, and in this case it's an AVX512 path, and a fallback pathway of the scalar code. And by reshaping the actions infrastructure, we've made it more dynamic and flexible and more performant. So as well as having this more efficient SIMD implementation of the actions, I also took a look at the scalar code path and I saw that there was some potential for small optimizations to be done. ODP execute actions is the function represented in the diagram here on the right hand side. And this is the part of the code where most of the actions are being handled. And essentially, this is a function with a very large switch statement containing about 20 different action cases. And each of the cases are going to handle the processing of specific actions. So a batch of packets will arrive and an action needs to be performed on them. And depending on the action, the switch is used to choose what function to call next, whether it be push a Vlan header, modify a MAC address, some other action. Now this branching caused by the switch it's costly in regards to performance and cycles and doesn't really allow for easy optimizations of individual actions. I also noticed that this switch was performing some loop inversions, and a loop inversion happens when a function is called inside a loop. So in the case of ODP execute actions, the relevant action function is being called inside a loop for each packet in a batch. And this is going to result in a call to the same function, passing the same arguments 32 times, which again, it's not very performant. So a solution I came up with for both these issues was to split the switch out into smaller per action functions and make those individual functions accept batches of packets. So in the diagram on the right, you can see that ODP execute action function has changed. So each individual case has now been pulled out of the switch and that they're now their own standalone function, which is going to accept a batch of packets. And inside the execute action function, a function pointer has been introduced, which in the diagram is the pink block labeled action selector. So this new function pointer now can call the smaller per action functions, and the benefits of refactoring the code this way will make it more performant. It's going to save some performance costs by eliminating the need to switch and removing the branching, and it will save even more costs by removing the function calls from inside the loop and making those individual action functions run per batch. And it's also going to allow for better testing of individual actions, and it's going to make the code easier for optimizing individual actions in the future. So along with this code refactor, I've also added support for a few commands to OVS AppKettle, specifically the dpif netdiv. The first one here, actions impl get, will return any available action implementation. And for each implementation, it'll say whether or not this is available on your CPU. And this is done by checking your CPU for some specific AVX512 flags. This command will also return which implementation is currently active, and by default, we're going to set this to the scalar code path. The second command introduced will allow the user to switch between the different implementations at runtime. So if you want to switch to the optimized path, you would run actions impl set AVX512, and if you want to switch back to the scalar implementation, you would run actions impl set scalar. So these commands are used to either get or set the OVS action function pointer to various different implementations like AVX512 or scalar based on the different CPU ISAs supported. And also as part of this patch series, unit tests have been added to test both these commands. Now there is a third implementation which I'm going to speak a bit more about next, and that is the Autovalidator. The Autovalidator approach was introduced previously into upstream OVS as part of the mini-flow extract optimizations done. And this approach is a form of automated testing and has been talked about in depth in previous OVS conference talks. Essentially, we're introducing new implementations of the actions and we basically have two implementations of the packet modification. And we really want to be sure of 100% correctness between both the scalar and the AVX512 implementations. We might be taking different steps to perform the action, but we still need the packet to come out the other end to be the exact same. So for this, we would call the Autovalidator implementation. Now, the Autovalidator is a great method for doing this type of testing. Firstly, it makes testing this patch series much easier. You won't have to go and make your test matrix twice as big for testing two different code paths, or more code paths if more implementations are added in the future. And secondly, it's a really good way to test for correctness. So the Autovalidator is going to run both the scalar code path as well as the optimized AVX512 code path and compare the results. And in this case, we want to compare the packet at the end of each run. So the Autovalidator will compare the packets by checking packet length, payload contents, as well as offsets or RSS values for each packet in a batch for each implementation. And by having this means and this level of testing, we can have confidence in the correctness of each implementation. So now I want to show an example of one of the actions I've implemented in SIMD and show the performance benefits of doing this in a wider register. So the first action implemented here is pop Vlan. So if you take a look at the top of the diagram, here you can see the packet header. And the first thing that happens is we start by loading the Ethernet and the Vlan headers into a single 128-bit register and combine that with another register of all zeros. So this leaves you with a temporary register containing the Ethernet header, a Vlan tag, and a bunch of zeros. So the next step is to perform an align write. And this basically will shift the Ethernet and Vlan header right by 12 bytes. And the result of that right-hand shift is taken, and we're going to store the low 16 bytes, which is the 14 bytes of Ethernet header plus 2 bytes of zero headroom. So when we store back that 128-bit register, we've essentially popped the Vlan in just 3 instructions. And after some initial benchmarking, it's going to save about 20 cycles per packet compared to the scalar way of popping a Vlan header. So pop Vlan action isn't quite done. There's still a few more steps to complete it, and that is to update the L2 offsets. And this has been implemented in SIMD by using an AVX512 K-mask subtract. So here is a graphical representation on how this new AVX512 version will work for updating the L2 packet offsets. In the top of the diagram here, you can see that an AVX512 broadcast is used. And for this, the scalar value of the Vlan header length, which is 4, is going to be broadcasted across a whole SIMD register. Then we load the 4 uint16 values from the DP packet into another SIMD register. And in this case, it's going to be the 4 offset values in the packet mbuf. Then we're going to use a K-mask subtract intrinsic to update the offset values of the packet buffer. And how this subtract is going to work is we take the register from the top of the diagram, the one where we broadcasted the Vlan header length to, and subtract that from the register containing the offset values from the packet. And based on the K-mask we provided, it's only going to update the L2, L3, and L4 offset values of the packet data. And these K-masks are really a major benefit of using AVX512 instructions. There's no other great way of conditionally turning on or off parts of a register. And they're really dynamic, and they're a really nice way of performing operations on only some bits of data in large registers like the ones we're using here. And they're also a really great way to write branch-free code to give some performance boosts. So we're going to take the resulting offsets from the K-mask subtract and store them back to that first register where we loaded them from. And essentially the packet offsets have now been updated, and that completes the entire pop Vlan action. So this SIMD version of performing the pop Vlan action, it's going to reduce the percentage of cycles used by roughly half compared to the scalar path of popping a Vlan header. So this work is being targeted for upstream in OVS 2.17, and we have sent a V1 to the mailing list, and we're welcoming reviews and comments. And once this series has been merged, next steps will be to investigate some more OVS actions and work on implementing them in SIMD to boost performance of even more actions. So thanks everyone for listening today, and if you have any questions, we can take them now, or please feel free to reach out to either myself or Harry. Our emails are shown on screen. And thanks again everyone for listening today.
And cut. Okay. I think that we have Harry here to answer questions. If anybody has questions, please post them to the Q&A panel. I don't see any yet, so I'll start out with sort of an observation of my own. I'd always kind of looked at how a lot of NIC cards have something they call Vlan acceleration, which basically pops or pushes a Vlan, and I always kind of laughed at it because pushing and popping Vlans is just not very expensive from a software point of view, and I'm kind of, well, I don't know if that's even true, because I mean you just showed us that you can do it faster, so is it your, I don't know, do you have any comments on that?
No, I think in general you're right. It's not very expensive for a CPU to do in software, absolutely not. At the same time, how optimally we can do it, can we optimize it and make it go even faster is kind of a different question. Is it worth pushing down to hardware? I guess it's such a common thing, and as you say, it's relatively easy to do. It's pushing a couple of bytes around. So I suppose the NIC folks also decided that it was quite easy to do, and given it's quite a common thing to do, they decided they'd do it in the NIC as well. So I guess that's one way to look at it. That said, the nice thing here about the SIMD interaction of this VLAN is that you can see how elegant really a solution can be in SIMD. That you load more data than you wanted, you smush it around to place a little inside a register, and then you store it back out and you overwrite the previous data that you loaded. So that kind of keeps everything nicely stacked on top of each other from a loads and stores perspective. So for anyone interested in microarchitecture, that's typically quite a good thing to do. And really, I like this idea that two things, I suppose. One, OVS gets more performance. That's definitely a good thing. But another is that software has an elegance to it, right? There's fun in writing elegant and nice software. And ultimately, I think that SIMD often has this, that you find a very efficient implementation that executes very well on a specific microarchitecture, but also there's just a craft to it. It's kind of like building something nice with Lego, that you have lots of instructions and you manipulate them in specific ways, and then as an end result, some compute has been performed, and the results that are stored out to memory actually match a different implementation that had potentially more cycles or more instructions or more UOPs required to achieve the same goal. So really, it's an optimization, right? It's an efficiency thing where you look at what work needs to be done, how you can do it, and then trying to match those in the most elegant way, or simple and elegant way often results in the highest performance.
Yeah. So I always find looking at how we can use basic instructions, basic data structures, and so on to make things efficient. I always find those to be really fun. There are some fun books on the topic. I don't know how many people here have read Hacker's Delight, for example. Despite the name, it's not about breaking into things. It's about a clever use of arithmetic and logical instructions to get things done fast. And I wonder if there will eventually be something that's sort of like Hacker's Delight, but for SIMD. And I think some of the things that you're starting to look at are kind of a fun demonstration of things that would fall into that category.
Yeah, I think you've just titled the next book that we can write, the Hacker's Delight SIMD edition. I like it. And definitely for packet processing, right? So there have been a few talks that, for example, Bruce Richardson, a colleague of mine in Intel as well, have done at FOSDEM last year around how we write duplicate PMDs and how that bit manipulation occurs in SIMD as well. We're getting a little off topic from the actions optimizations for OVS topic, but all the same, it's an interesting side topic perhaps.
So
in terms of, go ahead.
I was going to say that we do have a question now, but if you want to finish your thought, please go ahead.
Nope, I'll have a look at this question.
All right, so this is from Aaron Knoll, who says, some kinds of actions are a bit difficult to parallelize, such as contract, where the changes you make to the packet depend on the state changes, and you have to perhaps commit back some of those changes to the state. Can AVX and non-AVX implementations mix and match on a per action basis?
Yes, they can. Great question. So indeed, there are certain things that are just not the right type of problem to hit with the SIMD hammer, right? We have a particular way of solving problems, and if that way of solving a problem doesn't work well, then yes, we can mix and match. The way this has been implemented is very flexible, and Emma actually mentioned it in the talk, that there's a function pointer per action, and we're reworking the functions that implement each action and allowing a function pointer to it. So the default way that we will actually initialize OVS will have the exact same actions as scalar, and each function pointer will point at the scalar equivalent in its own function. And then one by one actions can be updated or switched to an AVX512 or other SIMD ISA implementation. And that's for two reasons. One, we can incrementally build these actions one by one. There's no change the world, all the actions are now running on a different ISA. For testing reasons, that's generally not a good approach. And the other is exactly this, that certain actions just won't be easy to optimize using SIMD. And for that reason, we can look at optimizing them using scalar code or using prefetch instructions, or there's a number of other ways to optimize software, right? It's not just about SIMD. And ultimately, we can see and mix and match to make OVS the best it possibly can be, given the CPU you're running on. Yeah.
Thanks. So we have a question from Valentine, who asks whether the SIMD implementations of actions will increment stats counters the same way as the scalar ones.
Great question. Yes, of course. So anything that we do inside the optimized versions of actions should and must have the exact same side effects or rather effects in general as the scalar implementation. So any changes that we make should not be visible to the outside world. And really that's important, and that's what the Autovalidator ensures. So the Autovalidator is the component that checks that the results are the same. And in some cases, what we'll probably do is try and use the generic function specialization trick that was mentioned in the last talk. If there are stats counters, we'll use a similar approach to ensure that stats counters are always incremented the same amount, or in the same by the same quantities, things like that. So absolutely yes, these must and have to be the same, and they will be the same, and we will use auto validation to ensure the correctness of the optimized.
All right, many thanks. Glad to hear that the effects will be the same. And thanks to everyone who spoke in this session, especially